All right, hello and welcome to my talk on fast incremental peg parsing. So first I'm going to give an overview of the paper and what this talk will be about. So we are able to improve the previous algorithm called Incremental Packrat Parsing for parsing expression grammars. So our improvements enable logarithmic time reparses rather than linear time. So we have much better scaling performance. And so in particular, our contributions are going to be three major improvements to the incremental packrat parsing presented at SLE 2017. Then we have some artifacts. So GPeg, which is our incremental parser, implemented as a parsing machine, and then Flare, which is a syntax highlighting library. And we also have an example text editor we use for evaluation, and in the long term, I'm hoping to add this to the micro text editor. Okay, so what are parsing expression grammars, and why are they? Why did we choose to use them? So pegs are sort of an alternative to context-free grammars that have some nice properties for us. So in particular, there's no ambiguity, and there's no lexing and parsing split. So this lack of lexing and parsing makes it easy to define a grammar because it's just one file. There's no sort of, you don't have to do multiple, you just parse using this one grammar. And then it's possible or easy to implement as a parsing machine. In fact, this has already been done. So the LPEG project was a good reference for us to build a parsing machine, and we want to use a parsing machine because it enables our parsers to be dynamically generated. So a parsing machine, you take a grammar, you compile it into a little mini language that you execute in a parsing machine interpreter. Fortunately, I don't have really time to go into this today, but you should definitely check out LPEG to learn more about parsing machines. And pegs are similarly powerful to context-free grammars, so we don't really lose anything in terms of the number of languages that we can parse. In fact, often we can parse more languages than context-free grammars. Okay, so these qualities make pegs good for text editors, but if we want to use a peg in a text editor, we're going to need to have an incremental parsing algorithm for the peg. Okay, so in particular, the reason that a peg is not ambiguous is that the choice operation, sort of P1 or P2, it requires that P1 is attempted before P2. So P1 must be attempted first, and only if P1 fails can P2 be attempted by the parser. Also, pegs have predicates, which I'm not going to go into much, but suffice to say they allow for unlimited look-ahead in the parser. Okay, so the arithmetic expressions, here's a grammar for them, and this also shows non-terminals and some recursion. Okay, so this example will come up later. Okay, so now we want to do incremental parsing. So this means that after each edit to the document, the reparse must be fast. We want to be faster than just doing a full parse from scratch. In fact, we want to be asymptotically faster than that. And so the previous solution was incremental packrat parsing, which adapts packrat parsing, which is a way of handling the unlimited look-ahead in pegs, making that more efficient, and it adapts that approach to an incremental setting. But unfortunately, since it's sort of making minimal modifications to the original packrat parsing approach, you only get a constant factor better. So maybe it's like 1,000 times better, but in the worst case, or in general, the reparse is still linear time. So as files get larger and larger, we're not going to be reparsing fast enough. So our contribution is going to be to sort of more fundamentally rethink the incremental packrat parsing algorithm to make it better tuned for incremental parsing in particular, and so we can get logarithmic reparse time for most edits. So now I'm going to explain incremental packrat parsing. So the key idea is to when the parser attempts to match a non-terminal at a certain position, we're going to save the result of that parsing that non-terminal. So maybe parsing that non-terminal at that position failed. We had a match failure, and in that case, we're going to save that result into our table, or maybe it succeeded, in which case we're going to save some information about how it succeeded into our table. And then if we ever try to reparse the non-terminal at that position, then we can reuse the information from our table to either know that the match will fail, or to skip ahead and just use the result that was saved into our table from the successful previous parse. So in particular, our table is going to map keys of these non-terminal and position pairs to entries, where an entry stores the length of a match or some special indicator that the match failed, and a possible result from the match. So maybe like some abstract syntax tree nodes, or maybe the string that was captured by that non-terminal. And then for incremental packrat parsing in particular, we're also going to store the number of characters that were examined to make the match. And this is going to become clear why we need this as I show an example of a reparse. But first I'm going to show an example of a full parse using packrat parsing. So we're going to use this arithmetic expressions grammar to parse an arithmetic expression shown here. And so when we start, the parser begins. It's going to attempt to match a number at 2, and it's going to succeed. Right, there's a digit here, so that is the one digit that corresponds to this number. But the parser also examined one additional character to check if there was another digit, and it found there was no other digit, so that's what ended the number. So we have some 1 byte that's part of the number, and then 1 byte additionally that was examined. Then we attempt to match a number at the parenthesis, but there is no digit here, so this failed. So we put in some indicator that we examined 1 byte and a number did not match. Next, we try to match a number again, and this succeeds. Again, we examine 1 character at the end. And then again, we do the same thing. Then the parser, here, according to the state of the parser, it knows that after parenthesis, there must be an operator, so it doesn't even attempt to match a number here. So we don't get anything, and then we attempt to match a number again, and we succeed. And then we're done. So we have this memoization table. Okay, so now let's suppose an edit occurs. So an edit is going to give us a range. We're going to remove the range of the text, and then it's going to insert some new text at eStart. And so how do we handle this edit? So back to our example, let's say that we're going to remove this range of 1 character of the multiplication symbol, and then we're going to insert +5. Okay, so when the edit occurs, the first step is going to be to remove all the entries that overlap with the edit, because those entries, any entry that has examined characters possibly modified by an edit is possibly no longer valid. So we cannot be saving that information any further. The other entries are fine. Their examined characters have not been modified, so we know that they are still valid. Okay, so now we're going to insert our +5 in, and then that in essence shifts our, we need to shift our memoization entries that come after the edit over, right? Because we removed 1 byte and inserted 2 bytes. So the start positions of these entries changed. Next, we do a reparse from scratch. So we start it just at 0. And then we use our Packrat parsing to read from the memoization table whenever we can skip something. So here we can skip a number. Here we can use the information that a number failed to match. And then we get to the 3. There's no information in our memoization table, so we just parse this number, and then we insert this number into a memoization table. Again, we're at the 5. There's no information in our table, and so we just parse this number again. And then we finish off by skipping this 300. And so this sort of 8 number entry stays in our table, but was not useful during the reparse. Okay, so in summary, we have 3 steps. We evict all the invalidated entries, we shift all the entries over, and then we reparse from scratch. The issue is all these steps are going to be linear time. And so now we're going to go through one by one to see how we can improve each of these steps to be much more efficient. So in particular, let's start with step 1. Step 1 is going to be linear time because if we're using a hash table or array for our memoization table, then we need to iterate through every entry to determine if it overlaps with the edit, to determine if it should be evicted. So the solution is going to be to instead use an interval tree for our memoization table. So if we store our memoization entries as intervals within the tree, then we get this nice query operation, which tells us if an interval overlaps with another interval, or it tells us all the intervals that overlap with a specified interval in logarithmic time. So we can feed in the edit interval as our query interval, and then determine all the memoization entries that overlap with it in logarithmic time, and that lets us evict all of them in logarithmic time. So that is going to be much more efficient. So that's a good fix for step 1. Now step 2, when we apply our shifts, if we have to iterate through every shift that occurred after the edit, that's worst case linear time. So that's going to be slow. So our solution is going to be to apply the shifts lazily to the intervals. So I'll show an example now. Here's our interval tree. So in each node, we store an interval, and we store the tree also stores the maximum endpoint of its subtree. So if we get, let's say, an operation that says insert 4 bytes at position 5, we don't actually do anything about this. We just insert it into a list of shifts, sort of pending shifts. We maybe get another operation that inserts a byte at position 2, and then again, we just insert it into our list of shifts. And now, only when we start doing the lookup do we start reading nodes and having to apply our shifts. So when we view this node, before we read any of its data, we need to make sure it is up to date with respect to our pending shifts. So we see that both shifts apply to this node because they both come before the node's starting point. So we apply both shifts by adding 5 to both endpoints, and now this node is blue and up to date. Next, we carry on down the tree, and again, now only one shift applies to this node, so we apply the shift, and the node is blue. And then for our last node, there is no shift that applies, but we still need to make sure, we still need to bring this node up to date. And so now all of our nodes are blue. which means they're all up to date. And these other nodes, if we ever view them, we would have to bring them up to date before we could return any information from them. And so these colors sort of indicate that in the implementation, you would need a timestamp per node to keep track of this information. Okay, the third step is going to be to reparse from scratch. This may also be a linear time operation because maybe we have a grammar that looks like this, sort of a syntax highlighting grammar, where there's at the top level a memoized p star. So when we parse using this grammar, we're going to get this sort of linear structure to our memoization table, where each of these entries is going to correspond to one token of the source code. And if we ever try to do an edit, so if we have an edit at this location, we're going to evict this entry in black and then reparse from scratch. And we end up skipping all of these tokens, which is great, but we still have to do a lookup for each skip. And so this is going to be a linear number of lookups because the number of tokens is proportional to the size of the file. And so we end up doing a lot of lookups, which can be costly. So the solution to this is going to be to use a new memoization strategy, specifically for the p star operation. So we want to sort of construct parent entries so that when we have small token entries, we insert parent entries that encompass both of them. And we want to do this in a tree manner, or sort of in a tree structure. So if I have this is the same file as before, but now our parser automatically inserted a bunch of parent entries. So when we saw sort of two one-token entries side by side, we inserted a two-token entry that covers both. And then when we have two token entries side by side, we inserted four-token entry, etc. And so we get this like doubling behavior, which gives us this tree structure. And this means that when we have an edit, for example, at this position, we're going to evict all these black entries, and then when we reparse from scratch, we only have to do lookups on these cyan entries, and that's going to that saves us from doing lookups on all of these blue entries. And we only do a logarithmic number of lookups, and that's going to save us a lot of time. So I just want to note here that there is some subtlety on reconstructing the tree as we do a reparse, and the paper talks about this more. Okay, so we also have some space optimizations that we do. We can do a threshold thanks to the tree memoization because now we have big parent entries being inserted automatically, so we can cut out small entries and reduce our memoization table size significantly. Also, if we have an application such as an editor that is only viewing a certain window of the text at a time, we can sort of, thanks to the separation and packrat parsing of the memoization table and the parse results, we can exclude all parse results that are not in the window, and that saves us a lot of space on the parse result size. So some evaluation. Here we can see that the initial parse time rises linearly, but our average reparse time, this is for syntax highlighting on a Java file, the average reparse time is staying roughly constant below 1 millisecond, even as we get up to a file that's 100 megabytes. In addition, our scaling for edits is also good, so there's no sort of degradation as the number of edits increases. The reparse time is staying constant, which is we also have similar scaling behavior to tree sitter, which is a well-known context-free grammar incremental parser generator. And then, sort of as a full application example, we have a text editor, and then here's some statistics on showing what the memory usage and reparse time was for a 51 megabyte Java file. So we stay below 5 milliseconds in general, including like redrawing the screen and handling the event. And then our memory usage is also, most of this is going to be the 51 megabyte actual file, and then it seems we have about 80 megabytes of actively used objects, and that's what the garbage collector runs every once in a while and removes all the garbage down to 80 megabytes. Okay, so in summary, the one-sentence summary is going to be that we've improved incremental packrat parsing with 3 new things. We use an interval tree, we use lazy shifts, and we use tree memoization to handle the linear repetition. Our implementation is available online, GPeg and Flare. And thank you to my advisor, Steve Chong, and thank you all for listening. If you have questions, there'll be a Q&A, or you can open an issue on GitHub or email me. All right, thank you.